you get number 3 correct? You have number 3 correct?
I thought we were supposed to solve it. Yeah, I figured out how to get the numbers, but I didn't know how to like put them in the equation.
So did you get a slope of a negative 1/3?
Yeah.
And did you get a y-intercept of negative 1? A b value of negative 1?
Yeah.
Okay, then it's a matter of sticking it into the equation. What's that?
I'm gonna have to move up because I can't see anything.
That's good. Then you want to be able to see. So Jackson, what was your comment? You understand the error that you made? Okay, but you guys, did you have different slopes and y-intercepts for number 3? So you had a different slope. Let me ask, what did you have for a slope? Over how much? Over 20. That seems too. And over 20.5. So let's just work on the board over here and work it out from the beginning, and then you compare your work to what we're doing up here and see if you can determine where your error was. So we have 2 points. We have a negative 1.5, comma, negative half, and negative 3, 0. So the steps with this is to take 2 points and find an equation from it. The steps are to first of all find the slope, and then use one of the points along with your slope in the equation to find the y-intercept. So in this case here, the slope is 0 subtract negative 0.5, and then negative 3 subtract negative 1.5. So subtracting a negative is like adding. So we have a half over negative 3 plus 1.5 is a negative 1.5. So then, to change that into a fraction to simplify it, I think that the easiest way to do it is to just multiply the top and the bottom by 10. And then you have 5 over 15, which is a third. So then when we write the slope with the negative, it goes into the numerator position. So there's your slope. Now, we are going to take that slope and we're going to plug it into this equation. So that goes in for m. And we are going to choose one of those 2 points to put into the equation as the x and the y value. I would use this one because it's not decimal numbers. Negative 3 and 0 is easier to work with than a negative 1.5 and a negative half. So that's the y, 0. That's the x, negative 3. So now you have an equation with one variable. And you have to solve it, and you have to find out what b is. So a negative times a negative is a positive, and a third times 3 is just 1. So this is plus 1. Now if you subtract 1, then b is equal to negative 1. So we have our slope, we have our y-intercept. Then you take those 2 and you plug it in to this equation. And this then is going to become y is equal to a negative 1/3 x, and then either plus negative 1 or just minus 1. That's your equation.
I'm just looking for a pencil. We're just going to put our names.
So then your question to yourself is, or it should be, where did I go wrong?
That's so great that those people were able to go get their
Where
cars.
did you go wrong?
The people on Beach Road were able to go get their cars.
You mixed up what, I'm sorry?
Roger put a road, a temporary road across the line, we wouldn't have to cars.
Oh, so you didn't copy the information down, so, okay, so did you do the work correctly, but with the wrong numbers? Oh, okay, how about you? Okay. So, this idea of, negative times a negative is a positive, that was, were you mixed up with some of that? Oh, okay, so it was just multiplication facts kind of idea. But you were trying to do the right steps, just got the wrong numbers, okay? Did you have the correct answer?
Yeah, I just didn't know how to put it into the equation.
Okay, so so that last step, pulling it all together and writing it in that equation. Did you get this one right?
Yeah, but I didn't.
Okay, pull it back into the equation? All right, well, that's good. I mean, if you can recognize where you made the errors, that's like the biggest step you can possibly make in math. Because once you recognize where the errors are that you've made and why you made them, then you can be conscious of that and correct it, and it gets better. So that's what we did. That's what this lesson is, Marvis. It's, I wrote out and I zipped off an email to Trenton.
Okay, so a lot of things make a lot more sense.
Do they?
Yeah.
Here, let me see if I can, and I also sent it to Tommy Griffin. Yeah, this right here, this is what I wrote. I wrote, find the slope from the 2 points, substitute into slope-intercept form the slope in place of x and the values of x and I from one of the points. Then write the equation and solve for b using inverse operations. So that's getting all the way down to this. And then once you have that, rewrite the slope-intercept form of the equation using the slope and the y-intercept, but leaving x and y in your final answer. That's how we do these. And I don't know, it shows up a lot, having to work with this kind of thing. So, what about, no, the answer is there. What are the answers? Where did I? Oh. That's not, they're not online, they're there, okay. How about the fifth one, number 5? Did we get the right slope? Yes. Get the right y-intercept? No. So we gotta figure out why. Did you get the right slope for that one? No. We gotta figure out why. So, you guys tell me. And you should be trying to work ahead, Marvis. Trying to be faster than us and trying to do these and see what you can do with them. So you tell me what to do. Okay, what should I write? Can speak a little louder. Between that fan, and my old ears, you gotta talk to me like I'm an old codger in an old folks' home. What should I write?
2 plus negative.
2
Minus.
plus or times? Or something else?
Minus.
Minus. 2 minus what?
Negative 3.
-3. So look at that. Can you think of that more easily? What should we think of negative?
Plus.
So that's just 2 plus 3. So that's 5. So your number sense, you guys, that's gotta become infallible. The closer you can get your number sense to be consistently correct, The easier it is to do the work. What are we gonna write on the bottom? Somebody else other than Leo. Say again? -8. What does that equal? -20. So simplify it. So you look at the fact that 5 goes in both of them. So divide by 5, top and bottom. 5 divided by 5 is? 20 divided by 5 is? And it's gotta be negative. Because a positive divided by a negative is a negative. So there's your slope. Now tell me what to do.
Y equals -1/4 x.
Plus b.
Yeah.
But now we need to have something else in here, so what should we do?
Use the point.
Which point do you want to use? It doesn't matter.
12
You want to use -12 and 2. So, tell me what to write if we use this one.
y equals -1/4 times -12 plus 2.
That's unlucky. These are points on a line with x and y values. So we should write 2 equals this times -12 plus b. Okay, then we have to simplify. 1/4 times 12. And it's a negative times a negative, so that ends up being a positive answer. 1/4 of 12.
3.
3. Plus b. So showing you these steps again. Then, we're not done. And then b will equal? All right. So now, we just have to go up here and either do that or say it's subtract 1. Either way. There's your answer. There's your equation. Okay. All right, we're going to keep moving. Next lesson. The next lesson is, this I hope you can remember from 7th and 8th grade. And let me just take a quick look at this and see what kind of graph paper I want to give you. Do you guys have graph paper yet? I know I give you some here and there. Do you still have pieces? Or would you like more? Yes. Are you okay? If you want more, come and get it. It's right here. Got a whole bunch. And let's see. So the next lesson is fitting a line to data. So the significance of all of this. Math is a language. I've told you that 100 times. Math is a language. It's a language that we use to describe what?
Value.
nature, the real world, the natural world. When you use words to describe things, you're just describing life, right? Things that are real in front of you are imaginary, but imaginary things are real too, because they're part of your real imagination. So when we write books, this is all describing stuff. You've got fiction, you've got nonfiction, you've got history, you've got mysteries, and you name all the different kinds of things that we can write about. That's all this reality that we live within. What math is just the other language. Math is a numerical language that is used to describe nature. So I say, well, they use it in science all the time. Well, science is the study of nature. But we use it in business, and that's a natural world also, the flow of money and trade and what have you. So what algebra is taking all this stuff that we see in nature and learning how to describe it with numbers, numerically. So we see patterns in nature, and we want to come up with a pattern in algebra, and the whole idea is to be able to predict. You know, for some people, it's nice to wake up in the morning and know what in the world the weather's going to be like. You know, like the other day they canceled the ferry. Why? They canceled the ferry because the weather was really, really bad. Well, they knew it was going to be bad, and they were planning on it. It's just a matter of waiting to see if the prediction held. But those are numerical models. And the data that we collect and we observe over and over and over is what gets used to make models for things. Models for medicine, models for weather, models for growing food, models for baking food, cooking food. You know, Dick Haas over there, he doesn't just say, well, let's put it in there for a little while and see what happens. It's all based upon collecting data and knowing how long it takes at certain temperatures to cook certain foods and stuff. So there's science to it. Whether you want to call it science or not, it's there. Everything we do is based upon patterns that we see. You live your life based upon patterns that are stored in your brain. Well, with math, we try to make these really concrete, really absolute, very dependable models. That's what you're learning the basic steps of in algebra, is how do we write models? Models are graphs, models are equations, and models are written descriptions. Models are data tables. So we spend a lot of time with data tables and graphs and equations, because that's what models patterns for us. But when they go and they collect data in the real world, you know, there's a professor that Mrs. Dagan had many times, and I had the opportunity to have once. His name's Kurt Larson, and he's a physics professor. He's great. He was awesome. And he would say something that is kind of funny. He says, well, nature's going to do what nature's going to do. We can have all the models in the world, all the predictions that are perfect, we think. And nature's going to be the way nature is. You can't change nature. And you hope your models are good. So with the slide over here out Beach Road, those geologists are trying to put together a model of what the side of that mountain is going to do in the next couple of years. But their models aren't going to be perfect, because the data that they collect isn't perfect. But they're going to do the best they can. And that's a real controversial thing, you know. But the bottom line is, nature's going to do what nature's going to do, regardless of whether our models are perfect or not. And there's lots of ways to do models. I talked to your grandfather once for 2 hours about this kind of stuff. And native ways of predicting and being able to come up with models seem to be different than this, but in the end, there are many, many things that are very, very similar as well. It's just how these models get put together. It's kind of interesting. That was an awesome conversation that we had. Well, the basics of all of this is taking these equations that we write with straight lines, and looking at data that seems to lay itself out in a straight line, and then saying, well, this is where the line should probably go given the data that we have. So here's what they do. They've got the life expectancy. And this is the life expectancy, I think, in the United States, because it certainly wouldn't be worldwide being at 77 years of age in the year 2000. So this is US life expectancy. And they've got this data table here. And they go every 10 years starting in 1930. So 1930, before or after World War II? Before. 1930s before World War II, after World War I. 1940, before or after? Beginning of. 1950, after. Before or after the Korean War? Before. 1960, after Korea, before Vietnam. 1970, towards the end of Vietnam, before Afghanistan and Iraq. 1980, before Afghanistan and Iraq. 1990, Iraq. 2000, Afghanistan, still sitting in Iraq. We could go and we could find 2010, Afghanistan. 2020, Afghanistan. We've been at war longer, most recently, than any time in human history, or US history. So, here's the year. Here's the life expectancy in years. In 1930, it was 59.7 years of age. Then it went to 62. You guys should be writing this down. 68.2. And if you took a piece of graph paper, if you have a piece of graph paper, and you put it like way over to the right, real neat and clean, it'll probably come out nice. Go work way over. Work with nothing any wider than maybe about 8 or 9 boxes.
From the table,
Yeah, make a table.
on the graph paper.
On the graph paper, you bet. Way over on the right edge. So then we've got 1960, that's the year I was born. 69.7. 70.8, look, it keeps going up, right? What do you think it is today? What do you think it is today? 85? Give me another guess, somebody. What do you think life expectancy is in the US today?
78.
Here it is, 2020. 78.9. 2020, 78.9. And the year 2010, 78.54. So we'll call it 78 and a half. What do you think it is this year? What do you think it is right now? 25. Current life expectancy in the United States is still 78.9. Hasn't changed. Last year, or the year before it actually went down. So for a couple of years it was going down for the first time in history. Big change here though, huh? And then it kind of just, it's flattened out, it hasn't changed just a whole lot. Antibiotics, made a big change. We got 63 to 68, 5-year jump in 1 year. Antibiotics. Penicillin, Okay, so now what we gotta do is we gotta put this onto a graph. My graph is gonna be a lot rougher than yours. So on your graph paper, you guys have your ruler? Vertical axis. So do you think we should put years for time or the years for life expectancy horizontally? What do you think should go across the bottom? Time, yeah. So this is gonna be the year. So here's what we're going to do. I would like you to, for example, think of the axis, the vertical axis, as 1900. And then every mark is gonna be 10 years. And then the life expectancy, the age, can go vertical. And I don't think that we need to have like from 0 all the way up. We should probably break the bottom of the graph. What do you think would be a good age to start with if we break this? So what I'm doing is every other line, I'm counting, or I'm labeling every other line, but every line is going to be worth 10 years going across. Look at the 0 in there. There it is. So what should we start at? If you break at the bottom, you want to start at age 55? And then can we get away with every line being 1 year? I mean, how many lines are there? There's like almost 40 lines vertically. So if we started at 55, we could probably get to 85. Can we do that? 55. Take a look at where you would put 55 on your graph. Your graph, that's not going to work. You need to go big. When you go big or go home. Yeah, we're going to go really big. Your axis should cover the whole page so that we can get a nice layout. That's probably going to work. So if you call that 55, count up and see if you can get to like 80 or so. Yours is got to be bigger. You got to go bigger. We need to go bigger. You should go bigger. That's why we need a big piece of graph paper. How high does it go?
Goes past 80.
It goes past 80?
If each line is one.
Yeah. Where's 80? Where's 80 come out to? 80 was here, so then you go. Yeah, so if you get towards the bottom of your paper, and then you do the little zigzag break here, and you start like that one at 55, then we ought to be able to make everything fit. So here's what I would want to do. Go to 56, 7, 8, 9, and then mark every 5. Like so. So if you mark every 5 and you get yourself to 80 or 85, we're going to be golden. can't zoom out any further, so this is what we get to see. So I'm calling this 1900, then that's 1910, and then there's 20, 30, 40, 50, 60, 80, 2000, 2020, oops, do it again, 2040. So the graphs should be right through here. And then if I call this 55, count up 6, 7, 8, 9, 60. That's what I'm doing. I went up as far as 80. Are we okay? Plot the points. 1930, 59.7. Keep on going. You don't need to label them, just put the points out there.
Yeah, but I think it's about that guy.
Yeah, I could bring that kind of stuff. It's like carpenters gotta bring hammers, right? Yeah. Do something really off color too, but I won't. But all the different professions, if they don't bring their tools, there's lots of different professions. Some of them are legit, some of them are not. So, there the points are. If we believe that this fits what we call a linear model, in other words, the equation is a straight line, like all these equations that we've been working with, y equals mx plus b. If we believe it does, we should be able to draw a straight line through it. Does it look like it does? No, it's got a curve to it, doesn't it? So you have to come back for subsequent classes, because what we can do is we could actually fit a curved model through it, but we have not worked with those kinds of equations yet. In nature, very few things are linear. Most things are curves. But to give you the idea of this, we have to start with these linear or straight models first. So then the idea is, let's just say it is linear. If it is linear, we got to figure out where that line is, and so it falls somewhere in between all of this data. Is that true? Or would it make sense to put it out here? Would that make sense? To draw a line out here and say, well, this is where the line is that data represents? You say no. How about if we put it up here? Would that make sense? What if you did something like this? Does that make sense to draw a line like this? No. So what you want to do is you want to figure out a way. If you got your long ruler, you can do what I'm kind of doing here and look at this. And you want to find some kind of a balance between the points. It seems like in the last, couple of decades, this is what the line would be, right? Up through here somewhere. And then these 2 points, these are points down here. They don't show up real nicely on the doc cam. But these are my 2 points down here for the 1930 and 40. So those are kind of like outside of what's been happening in the last number of decades. So if I was to do this, I would probably, and I want you to do the same thing. Maybe we ignore 1930 and 40, and then we say somewhere in here is where our line is. And I didn't do a good job, because see, I've got more points above the line than below the line. You might be able to do a better job. The idea is to have a balance all the way across here. But the key to this is once you draw a line like this, what we do is we kind of transition over and we say the line is what we use for making predictions. The line is what we use for determining slope. We don't use the points any longer. We would use the actual line and points that are on the line. So if this is the best I can do, I'm going to say that's where it is. I'd like you to put a line on yours. And then maybe extend it so that it takes on a couple more decades of time, since you guys are going to be here for a while. Not literally here, but you're going to be around for a while. So this line, when we put it on here, it's called a line of best fit. Another name is it's a least squares line. And then another name that's given to this is a regression line. Regression is what you're going to hear a lot because it's something we can do on the calculator. If you took a look at this line, each of these points, I'm going to zoom in. Each of the points for your line, for my line, is off by a little bit from the line that I put on here. So if I looked at this point, for this year, which is, what is this, goes all the way down, this is 1980. The actual data is this value here. But the line would say that it's this value here. So it's off by a little bit. The line is off. And if you were to do this, if you were to make a box where you said this is how far off, and made your square the same width as the height as that point is that's off, you have a little square here. Here, the same thing. you've got a little square that shows how far off. Here's a different size square. Up here is a really little square. If this line extended way down here, this would be a huge square, right? Showing that the data is really far off. And one of the ways that mathematicians and statisticians are able to analyze these lines is they figure out how far each point is away from the actual line, and they square that number, and then they add everything up. They add all of those squared numbers. So when they add all those squared numbers up, the idea is that the smaller the number is, the smaller that the value is, the closer the line is to the data points, and the more accurate the line is. The whole idea is how accurate is the prediction? How close are we? And this is mathematically how it ends up getting done. So tomorrow, make sure that you bring your graphing calculator. Don't bring your phone as a calculator. Make sure you have it. And I'll show you how to work with this kind of stuff in the graphing calculator to make life easier than what we did on paper. What I'd like you to do for tomorrow, though, is this Lesson Master 6.6b. I would like you to attempt to finish it, front and back. And this graph